Hello everyone. So we are in the third part of the subtopic surface tension, where it is today's lecture. We're going to discuss excess pressure within air bubbles. So welcome to IIT-JAM in Chemistry tutorial number 26, and this is the lecture number 4 of the physical chemistry chapter, liquid state. So we all are acquainted with such pictures where kids are playing with soap bubbles. So what about the excess pressure within these soap bubbles? Okay, so this soap bubble is made up with some liquid. Here it's soap water or shampoo water, and with the help of surface tension we can calculate the excess pressure within these soap bubbles. So let's start. Here this is a hemisphere, which is actually half a soap bubble or half a free air bubble, where we have cut this through this central line, where the circumference is appearing like this, a circle, and this is the center of gravity, where two opposing forces are cancelling each other, and these are at equilibrium. So at equilibrium these opposite forces are equal. So what about these forces? One force is due to pressure in the upward direction, another force is due to surface tension of the liquid in the downward direction, and at equilibrium these two are same. Let's calculate. Suppose the radius of this soap bubble is r, and surface tension of this overall liquid is gamma, and the excess air pressure, that is, it has some atmospheric pressure which is inside and outside same, but inside this bubble there is some excess pressure other than that atmospheric pressure, and this is small letter p. We have to calculate that one. Now the upward force. So this force is only due to this excess pressure, because the atmospheric pressure outside and inside cancel each other. So which force is left in the upward direction? Only the force due to excess pressure in the upward direction. So if P is the pressure and r is the radius of this disk, then pi r squared is the surface area of this disk. Then pressure times surface area is force. So if we convert this into the dimension of force, then we have to multiply pressure with the surface area. So it is P, the pressure, into pi r squared, the surface area. So this is pressure times area, P pi r squared. Okay. Now the downward force. This downward force is due to surface tension. This tension is playing along this line of circumference. It is playing along the perpendicular direction. Suppose these lines are hanging here. These arrows are showing the forces due to surface tension. Now surface tension also does not have the dimension of force, so we have to convert this into the dimension of force, but just by multiplying this with length. So what is the length? Length is the circumference of this hemisphere. So the downward force due to surface tension is the circumference twice gamma r, twice pi r into the surface tension gamma. Now here is another factor 2. 2 is multiplied here with this force, because there are two surfaces. One is the upper surface, another is the inner surface. That means one is the outer surface, another is the inner surface. So due to these two surfaces, this surface tension becomes doubled. That is why this 2 factor is multiplied here. So instead of being it is twice pi r gamma, it is actually 4 pi r gamma. So the downward force due to surface tension is 4 pi r gamma. And at equilibrium, these two forces are equal, upward force equal to downward force. That means P pi r squared equal to 4 pi r gamma. That means P, small letter p, is 4 gamma over r. So this is equation number 6 as continuation from the previous equations. So this is one relationship where the excess pressure is 4 gamma over r, 4 gamma by r. This is the excess pressure. Then what should be the overall pressure? Actually, the atmospheric pressure is P, which is also present inside the bubble. So we have to add these two. So small p added with capital P, that means capital P plus 4 gamma by r. So this is the overall pressure inside the bubble. But what is the excess pressure? Excess pressure is only 4 gamma by R. Now look at this picture. Here also air bubbles are formed. But the fact is that these air bubbles are within this liquid, not they are moving freely in the air. And the criteria of these air bubbles, they have only one surface, only the inner surface. They do not have the outer surface. Let's consider like this. So look, this is an air bubble which is at the depth h from the surface, and this liquid has density rho and surface tension gamma, and P is as usual atmospheric pressure in the which is capital P, and it is above the surface of the liquid which is the atmosphere actually. Also this pressure is present within the air bubble also. So this P in the atmosphere and P within the air bubble within the liquid are equal, and these two cancel each other. Then what is the excess pressure? There are two pressures here. Here not only one pressure, there are two pressures. Let's discuss how. So these descriptions are as usual. The radius of the bubble is R, surface tension is gamma, excess pressure instead of small p. Actually the small p was used in the previous pre-air bubble, so this is P prime, just to show the difference. And now what is the upward force? Look, upward force, actually we have to consider here the hemisphere also, and upward force must be calculated by the same way. That means the pressure into surface area of the disk. So pressure is, excess pressure is P prime, and the surface area of the disk is pi r squared. So it is P prime pi r squared. What about the downward force, which is due to surface tension? Downward force due to surface tension is actually circumference into surface tension, because surface tension is, again I say that it is not in the dimension of force. So if we want to convert this into the dimension of force, we have to multiply this with the circumference of the hemisphere here, from here to here. This is the circle. Look at the movement of the cursor. This is the circle. So the length of the circle is actually its circumference, which is twice pi r. So it is twice pi r gamma. At equilibrium these two are equal. Okay, and after calculation we get equation number 7. So P prime is twice gamma by r. In equation number 6, what we got? We got 4 gamma by r, but here it is twice gamma by r. So this is just half. It is only due to one surface, only the inner surface. So it becomes doubled if it has two surfaces in the free air bubble. Now as I have said that there are two forces apart from this force, and this force is the force due to depth of the bubble. The bubble is at some depth h, where the liquid also inserting some pressure on that bubble. That is also present within this bubble. What is the value? It is h rho g. We know this equation. H is the depth, rho is the density, and g is gravitational acceleration. And these two are actually the excess pressure. And atmospheric pressure I have already mentioned. This is already present there. So the overall pressure is not capital P plus twice gamma by r. The overall pressure, you have to add one more factor, which is h rho g. So the overall pressure within this liquid bubble, within this air bubble, is capital P, that is the atmospheric pressure, plus h rho g plus twice gamma by r. So this is the overall pressure for an air bubble within a liquid. Now, hemispherical depression due to capillary rise. Okay. We have already done the calculation of capillary rise, and this is kind of verification. We have done already, right now calculated an air bubble within the liquid. This can also be applied in calculating the hemispherical depression without accurate treatment of capillary rise. In the previous lecture, the second part of surface tension, that was lecture number 3 of liquid state, where we have seen different types of spatial cases, and the accurate equation also we have derived. So we have to arrive at such an equation which we have to check whether this matches with those equations. Okay, so this is a hemispherical depression. This is the meniscus, and the height of the meniscus is h. So the pressure of the liquid is h rho g. Now we have calculated this excess pressure as twice gamma by r just now. Equation number 7. Look at this. No, not that. This is the equation number 7. This is the equation number 7. It is twice gamma by r, isn't it? Look. Now excess pressure due to surface tension. This excess pressure, this pressure is playing the role in this direction from here to here along the wall of the capillary, here to here, and through the circumference of this hemisphere, of this meniscus. Now this upward pull is balanced by the downward pull due to the gravitational pull of the liquid. So at equilibrium these two are equal. Now the downward pull, as I have mentioned, it is h rho g. Rho is the density of this liquid. Therefore the pressure P prime is h rho g. Then what about the upward force? You know that is twice gamma by r. So twice gamma by r must be equal to h rho g. Therefore the value of gamma must be half h rho g into r. Now this is not equation number 8. Actually we have already derived this equation. Where? Look at this slide. This slide was used in the previous lecture where we have made accurate treatment for capillary rise. This was the exact equation. But if theta is taken to be, that contact angle is taken to be 0, and the weight of the liquid within this meniscus has been neglected, then the equation 5c was derived. Okay, gamma equals to half h rho g r. Now move on to the previous slide. Here gamma equals to half h rho g r. So this is cross verification whether our calculation for an air bubble within a liquid was correct. So that's all about the third lecture. Now let's discuss some question. If the total air pressure within a free soap bubble of radius 4 mm is 1.0006 atmosphere, then the surface tension of soap water is what? Now in order to calculate the surface tension, you have to round it up to the second place after the decimal, and after that you can also multiply 10 to the power minus 2. That means the answer should be in Newton per meter in such a way that the answer must be something 0.2 decimals into 10 to the power minus 2. Okay, so let's calculate. For a free soap bubble, the total air pressure. What is the total air pressure? It is actually the atmospheric pressure plus the excess pressure. So excess pressure plus atmospheric pressure. Now atmospheric pressure is 1 atmosphere. So what is the excess pressure? It is overall pressure minus 1, isn't it? So this pressure is the overall pressure. This is the summation of atmospheric pressure and excess pressure. And this is 1.0006. Excess pressure P, this is 1.0006. 1 is deducted from here, so the excess pressure is 0.0006 atmosphere. And if we multiply this with 101325, then it will be converted into the unit of Newton per meter square, because we know that 1 atmospheric pressure is 101325 Newton per meter squared. Now we know, since this is a free air bubble, so the formula must be excess pressure is 4 gamma by r. So let's rearrange this equation in order to calculate the surface tension gamma. Then gamma must be equal to PR by 4. Now let's put the values. The value of pressure is 101325 into 0.0006 Newton per meter squared into the radius, which is 4 millimeter. So you have to convert this into meter. So 4 into 10 to the minus 3 meter divided by 4, and the result is up to the second place of decimal 6.08 into 10 to the power minus 2 Newton per meter. So we have to put just 6.08 here. Move on to the next question, question number 5, and the question is, the radius of a given capillary is 1.05 into 10 to the power minus 4 meter. A liquid with density 800 kg per meter cube rises in the capillary up to a height of 6.25 into 10 to the power minus 2 meter. Assuming the contact angle of the liquid to be 0, its surface tension is what? So same way, after having rounded off, rounded up to the second place of decimal and giving 10 to the minus 2, you have to calculate this into by Newton per meter. What's the answer? So we have to collect the data. We have to compute the data first. The radius is 1.05 into 10 to the power minus 4 meters. So it is SI unit. It's okay, no problem. The density also given in the SI unit, 800 kg per meter cube. And the height is also given in the SI unit, 6.25 into 10 to the power minus 2 meter. So what is the value of gamma? So it will be directly obtained in the Newton per meter unit. So this is actually capillary rise and the special case of hemispherical depression, just we have seen in the equation number 5c. So we have to use this formula. So this is the equation, gamma equals to half HR rho g, where g is the gravitational acceleration and it has the value in the SI unit is 9.81 meter per second squared. So the value of gamma, just having put the values, the value of h, the value of r, the value of rho, and the value of g, we have finally got this value, 0.02575 Newton per meter squared. So after giving 10 to the power minus 2 and to the second place of decimal, it is rounded up 2.575 and rounded up to 2.58. So the answer is 2.58 into 10 to the power minus 2 Newton per meter. So that's all for this lecture. Thank you. Have a nice day.